Hello my YouTube friends, welcome to my channel, and today we discuss second order transient circuits. We look at the theory, and then in the next video we'll look at a few examples. Now let's get into understanding what second order circuits are. So any circuit with a single resistor, a capacitor, and an inductor with a number of sources, a number of resistances is deemed or defined as a second order. So you've got a resistor, capacitor, inductor connected. They may be in series connection. We have the series, and we also have the parallel connection. But this is all going to give us a second order differential equation, and that is why we call these circuits second order circuits. So when we look at applying KVL in that series circuit, we find that we're going to have a potential across the inductor, the resistor, the capacitor, and then we've also got a potential which we call the initial value of the capacitor in that circuit, and then that must be able to give us the source value at t. And when we get these values in terms of integral differential equations, then what we obtain is the inductor value of the voltage is L di dt, dit at dt, plus this is the voltage across the resistor, and then this is the voltage that we have across the capacitor, which is 1 over C 0 to t I t dt, and plus the initial value of the capacitor should be able to give us the source value at t. And we have to convert these circuits into purely differential equations for us to be able to solve. And therefore, when you convert this into a purely differential equation, we obtain 1 over C I at t. And then here we have a second order differential which comes in place because we already had first order differential equation there. So d squared I at t dt squared multiplied by L, and then here we've got R dit at dt, and this should give us the forcing function, what we call the forcing function, dvst over dt. And using these terminologies, we now come up with a few terms that we need to explain. So we want to get to this equation have a purely second order differential, and what we do is we divide this circuit by these terminologies by L, and when we divide by L here, we've got everything is cancelled out. So L is cancelled out. Here we remain with R over L, 1 over C L on this side. And this is what we obtain in the next slide that I'm showing here. So we obtain 1 R over L here, and then we've got 1 over LC I at t, 1 over L as the forcing function. And then when we begin to incorporate terminologies that assist us in simplifying these second order differential equations, one of which is the damping coefficient, which is alpha to be equal to R over 2L, and then we've got the undamped resonant frequency, which is omega naught, which is 1 over the square root of LC. Bear in mind that these terminologies may be slightly different when we look at parallel connection of circuits, but we're looking at the series circuit, and therefore this section of the equation is what we call the forcing function, and this is the forcing function. And using these identifiers, or rather definitions that we've put up, we're able to simplify our equation to appear in this format, where we replace in the previous equation with 2 alpha, and then here we replace with omega naught squared I at t equal to the forcing function ft. And then we have to able to now define this equation accordingly and understand how we obtain the solution. So the solution that we are going to obtain is going to be obtained with two components. One is what we call the particular solution, and the second component is called the complementary solution. And the complementary solution has got three cases that we'll discuss just now. But to find the particular solution, we have to find, and by the way, in this equation we are saying x at t could represent a voltage or a current, depending on what we are looking for. And so if we are looking at now finding the solutions, then we have to find the particular solution, or what we call the forced response solution. And this depends on what circuit type you're dealing with. If you are dealing with a DC circuit, then it's easier to find the particular solution because we just simply replace the inductances by short circuits, and then we replace the capacitances by open circuits, and we solve. But then in this case, we're looking at a DC circuit, and we want to use these further as examples. Now, for us to obtain the complementary solution, for the complementary solution, we have to take the equation as a homogeneous solution equation and find the homogeneous equation solution, which in this case we are saying we substitute the forcing function by 0, which creates the homogeneous equation. And therefore what we find by taking an estimation, or what we call a trial solution, in this case xc at t, which is the homogeneous solution here, we estimate it to be equal to ke exponential st. This provides, if we replace this into all the variables of xc at t, we obtain the solution s squared kest plus 2 alpha s kest plus omega naught kest equal to 0. And when we factor out what is common, which is in this case kest, we obtain s squared plus 2 alpha s plus omega naught squared kest, which gives us 0. And further, what we must notice or take note is that kest must be non-zero, must not be equal to 0. And if it is non-zero, therefore we obtain our solution to be, or rather the equation to be s squared plus 2 alpha s plus omega naught squared equal to 0. And this is what we call as our characteristic equation. And the complementary solution depends on this characteristic equation, especially depends on what we call the damping ratio zeta, which is the ratio between the damping, the alpha, and the omega naught, in this case being equal to zeta. And once we know what this ratio is, we've got three case scenarios that assist us in finding the complementary solution. First of all, what we notice is that there are only three case scenarios that we can obtain. Is either we have our zeta is greater than, so case 1 is we've got zeta greater than 1, so which is greater than 1, and then we've got zeta equal to 1, and then we've got zeta is less than 1. And these are the three case scenarios that assist us in understanding or finding the complementary solution. When we look at case 1 here, this case is what we call the overdamped case. In this case, we've got zeta greater than 1. And if zeta is greater than 1, it's the same as alpha, or the damping coefficient, being greater than the underdamped coefficient, which, the underdamped resonant frequency omega naught. And therefore, the roots of the characteristic equation, which I showed you, the roots to the characteristic equation, which is this equation, are going to be, in this case, real and distinct. So this implies that the solution xc at t is going to be equal to k1 e s1 at t plus k2 e s2 at t, and the circuit is said to be overdamped. Now, what is overdamped, or what does this imply? Overdamped case implies that response is going to take longer to reach steady state, as you can see. So it's overdamped, is going to take longer to reach steady state values. And this can be seen if we square both sides of this ratio or comparison, alpha and omega naught, we get to find that the resistor value is going to be much larger in this circuit. And then the larger the resistor, the greater the damping in the circuit. Now, a larger capacitor will not impede the flow of current, so still a lot of current to be allowed to flow in the circuit. So you've got a capacitor value which is large capacitor as compared to these other values. And then you have got a smaller inductor. In this case, the inductance value will be smaller than that. So all these scenarios allow for the overdamping. When you've got a larger resistance, a larger capacitance, then you're going to experience overdamping in the circuit and the smaller value of inductance. And this is not very good if you're doing adding a solar system into a grid, for instance, because what you need is for the damping to be very quick, so that you lessen the transients in the circuit or in the grid. And the other scenario that we obtain is when zeta is equal to 1 or alpha is equal to omega naught. This is the case that we call the critically damped circuit. And in the critically damped circuit, the roots to the characteristic equation are real and equal. So you've got the same, if you notice, you've got the same S values, S1 there, because the roots are equal. And then this is the solution that you obtain in the case where the circuit is critically damped. And what critically damped implies or means is that when we come to analyzing or damping a circuit, critically damped response reaches steady state the fastest, and it has no oscillations. As you can see, it is very quick and stabilizes very quickly. So it is, if you are adding a grid, if you're adding any distributed generation system into the grid, then you are looking at obtaining at least critically damped scenario for you to quickly reach steady state values, and that lessens the disturbance in the general system or grid system. And again, if we compare the ratios, if they are equal, you find that the resistance value here is going to be equal to this value. The capacitance value is going to be equal to that. The inductance value is going to be equal to that. More or less a balanced system. But the last case scenario that you obtain, we call it the underdamped scenario. And this is the case number 3, when zeta is less than 1, or when alpha is less than omega naught. In this case, we call it the underdamped case, and zeta is less than 1. And the roots that we obtain in this scenario are complex roots. And to obtain this complex root, you notice that in these complex roots, you have a natural frequency omega n, which is obtained by the square root of omega naught squared minus alpha squared. And this natural frequency is a frequency that every object has. If we look at vibration, each object is vibrating at a natural frequency. And So this is important in that underdamped case. But in the underdamped case, the solution that we obtain is a complex frequency solution, and this is what we obtain, which is multiplied by the cos omega n at t, and here we have got the sine omega n at t, and this implies that we are going to have oscillations in the damping, and when we come to analyzing, these are the oscillations that we obtain in the damping of this circuit. And because of the oscillations, this takes a long time to reach a steady state, and the underdamped response is not a response that you are looking for if you are doing grid integration studies and you are trying to integrate a solar system or a solar station or a wind station into the main grid. And you notice that in this case you're going to have large inductance which opposes the flow, the change of current, and then the current will now oscillate about the zero axis in this case, which is the steady state axis. It will oscillate about this axis for a long time, but eventually it will get to steady state values or to zero. And we'll look at the examples in the next video. Thank you for joining me, and thank you for watching. If you have any questions, you are free to add questions on the comment section. We'll discuss the examples. I'm sure the examples will make it more clear for you to understand the second order transient circuits, which are very interesting because now we're looking at more or less the real scenario in integration of or grid studies for integration of distributed generation system into the grid. Thank you. Good day.